So as we have seen, if you find a function that stays above the indicator function, you can find a bound for this non-negative random variable x. And we have seen now that for positive s, the function e to the power s times x minus a stays above the indicator function of x greater than or equal to a. Therefore, we can use it to derive a bound on this probability. Okay, so the probability can be written like this and replace the indicator function here by this function e to the power s times x minus a. Then what you get is, you see, e to the power, well, this is, again, this should be 0, sorry about this, 0 to infinity, e to the power minus sa times e to the power sx, the PDF dx. Okay, now you see this term does not depend on x. Therefore, I can pull it out of the integration. And the remainder gives me the expected value of this function, e to the power s times x. Okay, it's in fact a generating function, sort of generating function. So what we get is the expected value of e to the power s times random variable x divided by e to the power s times a. Now, you see, this holds for all non-negative s values. Okay, that was our assumption, because, well, any non-negative s, this function will have this shape. So it will stay above the indicator function. Therefore, this inequality holds for, well, this inequality here, greater than or equal to a, is less than e to the power, expected value of e to the power s times x over e to the power s times a. This a is this a here. And you see, s is free variable here. Any s value here that is non-negative works. So I would like to find an s value that minimizes this value here, so that I have the tightest possible bound. Okay, that's the power of Chernoff bounds. You can make it smaller and smaller by choosing the s value smarter, in a smart way. So how to do that? Well, obviously, you just find an expression here and differentiate it with respect to s, equate it to 0, and solve it for s equals s greater than or equal to 0, and then you find the s value that minimizes that expression. Okay, so this is the uh, expression of Chernoff bounds. But, well, here I give an alternative derivation. Essentially, since we assume s is non-negative, the event that x is greater than or equal to a is essentially equivalent to the event e to the power s times x is greater than or equal to e to the power s times a. Because you see, when you have this inequality, obviously for non-negative s, you can write s times x greater than or equal to s times a. And then you can exponentiate both sides, because exponential function is a monotone function, right? When the input increases, the function value also increases. So if you exponentiate both sides, the inequality does not change direction. Okay, it's preserved. So this event is equivalent to this event, so they have the same probabilities. And now here you see e to the power s times x, since s is, well, it doesn't really matter what s is, the exponential function is a non-negative function for any value of the exponent. This is never negative. So if you define this as a new random variable y, you can apply Markov's inequality to y, right? This is y greater than or equal to, well, e to the power sa, some value, which is positive. Okay, so apply Markov's inequality, you get expected value of y, which is this, divided by this number here. So you get Chernoff bound. And then, as I said, you optimize this bound by minimizing it. Now let me show this on an example. And in this example, first we will derive the Chernoff bound for a Gaussian random variable with a mean of mu and the variance of sigma square. Okay. Now here we will put a bound on this probability x exceeding a. And of course, well, we know this to be equal to the Q function evaluated at a minus mu divided by sigma. But for whatever reason, maybe you don't have access to a table, maybe you do not have a tool to implement or to solve the Q function for whatever reason, you might want to put a bound on this value. So what you do is, first of all, you need this, and this here you see appears here, e to the power s minus s times a, and this here can be computed through the characteristic function. If you remember, the characteristic function was defined as the expected value of e to the power j omega x. Now here, if you just plug in, instead of w, if you plug in minus js, you get expected value of e to the power sx.